Hi, my name is Kyle Schomp, and I'm going to briefly introduce you to Akamai DNS. Akamai DNS is an authoritative DNS infrastructure. And to illustrate what that is, I'm going to use the example of you or I as an end user trying to fetch some web page on our laptop. So we type in a URL, right? And the first thing our browser is going to do is it's going to try to resolve the host name of that URL to an IP address. So it's going to send a query to a recursive resolver. And that recursive resolver, assuming it doesn't have the answer in its cache, is going to go out and query authoritative name servers. And these authoritative name servers could belong to multiple different authoritative DNS infrastructures, right? One of which is Akamai DNS. After it queries one or more of these, it'll get an answer, and it will return it to you on your laptop, and then you can actually go out and fetch whatever content it is that you actually wanted to view in the first place. So this entire interaction, including Akamai DNS, really prefaces the content fetching that we're interested in as users. Akamai DNS on a typical week, or a typical day even, is serving millions of queries per second on average. And these queries that it's answering are for the Akamai Content Delivery Network first, or the CDN. As such, Akamai DNS prefaces every fetch for content that's served by the CDN. But it's also for various other domains that enterprises choose to host on Akamai DNS. And these domains can run the range of services that are available on the internet. As such, Akamai DNS is a starting point for a significant fraction of the world's internet interactions. And therefore, we view it as having a critical role in the internet ecosystem, because if anything were to happen to Akamai DNS, if it were to go down, a large portion of the internet would not be available. Therefore, we take great care to make sure that Akamai DNS is always available, and we, in particular, design our systems to be highly resilient to failures of any kind and attacks that we may experience. And that's primarily what I'm going to talk about today. So let's dig into Akamai DNS a bit more. Let's see what's under this cloud here. First, we're deployed globally around the world in over 157 different countries. And each one of these POPs, or points of presence, contains our authoritative name servers. So there are 157 different countries covered, of course, and I'm just showing you sort of a toy example on the slide here. Between these POPs, we use IP Anycast to load balance the DNS traffic we receive. This means, of course, that we advertise the same IP prefix for multiple different POPs, and then BGP best path selection determines where recursive resolvers get routed to. For example, this recursive resolver in India might end up being routed to Singapore when it sends traffic to Akamai DNS. At a lower level of detail, though, Akamai DNS actually uses multiple Anycast prefixes, and I'm going to illustrate them as A through G on this slide, color-coded, right? We advertise each one of these Anycast prefixes from different POPs around the world. So here's an example deployment, right? You can see that A is advertised from 4 POPs, B advertised from 3, and so on and so forth. No POP advertises more than 2 of these Anycast prefixes. But what this means, again, using our Indian recursive resolver as an example, is that when querying Akamai DNS, the recursive resolver has options, right? It can query any one of these Anycast prefixes, be routed along a different path to a different POP with a different capacity in name servers residing within that POP. This has a couple of nice properties for it for our resiliency. And to talk about them, I'm going to use 2 domains. Example1.com is delegated to A through F, so to 6 of these Anycast prefixes. And then example2.com is delegated to A through E plus G. So their delegation set is off by 1. And we do this for all domains that are hosted on Akamai DNS. They all have a slightly different delegation set. So thinking just about example1.com first, this means that if any 5 of these POPs are down, the recursive resolver can still obtain an answer for any query under example1.com, right? In this case, it can use the F delegation. And what could cause the other POPs to be down, right? Possible examples is widespread failures, routing issues, or even attacks that are consuming the entire capacity available in those POPs, rendering them incapable of actually responding to legitimate DNS queries that they would receive, like those from our Indian recursive resolver. Going a step further though, even in the worst case scenario, for example 1.com, where all 6 of the POPs here are unable to answer DNS queries, the recursive resolver in India can still obtain answers for example 2.com using the G delegation. And this is the compartmentalization within our infrastructure that we use to guarantee, even if under a widespread failure for one of the domains supported by Akamai DNS, other domains supported by Akamai DNS are still available and we are still able to answer queries for them. Let's drill a little deeper then and look at the architecture of just one of these POPs in more detail. And it's pretty simple. POPs consist roughly of a router and then one or more racks of machines behind that router. I'm illustrating just 2 machines here on the slide for simplicity, but in reality there would be many more than this. Each one of these machines runs our authoritative name server, which answers the DNS queries, but also a couple of other processes. First, a BGP speaker, and this BGP speaker actually is the originator of all of our advertisements for our Anycast prefixes. And then a monitoring agent, which instructs the BGP speaker whether or not it should advertise based upon the health of the name server. So let's assume first that the name server is healthy. The BGP speaker is advertising, and it's advertising to the router. The router receives these in advertisements from the different machines in the POP, and then advertises again the Anycast prefixes out to peers. And in the reverse direction, DNS traffic then flows into the POP, right? And the router spreads it roughly uniformly among the machines within the POP. So this architecture allows us to do a couple of useful things with failure mitigation. Let's say, for example, that the top name server fails in some way. It could be that the name server software itself crashes, maybe it's answering DNS queries incorrectly or something like that. The monitoring agent is going to detect this issue, and there are more details on how it does that in the paper. But once it detects it, it's going to instruct the BGP speaker to withdraw the BGP advertisement of the Anycast prefixes. At this point now, the router will no longer have an advertisement from the top machine, so all DNS traffic flowing into the POP will be routed to the bottom machine. And we've effectively failed over between machines within the POP, right? However, if there's a failure with the bottom machine as well, it will also withdraw its BGP advertisements as well from the router, and the router will then withdraw the advertisements from its peers. And all traffic now, DNS traffic, will flow to other POPs advertising the same Anycast prefixes. And we've effectively at this point failed over between POPs. The failover between machines within a POP is more or less instantaneous, but failover between POPs can take on the order of a second, and we have some measurements in the paper that I encourage you to please take a look at. So this general mitigation strategy works for a wide range of failures, but not all. Consider one example. Consider an input-induced crash, right? So the name servers need inputs, of course, to answer DNS queries. And thinking about that one POP, right? If both of the name servers in that POP crash, then the POP will withdraw its advertisements and will effectively be taken offline, right? But of course, all of the name servers are consuming these inputs. So if they all do the same, all of our POPs will be taken offline and Akamai DNS will no longer be available. But so Akamai DNS will no longer be available, right? That's clearly unacceptable. Even in an extreme scenario of an input-induced failure that causes crashes, we have to be available. We have to always be up, right? So we have another mitigation strategy designed to deal with this particular type of issue. And we have special name servers. So you'll notice the bottom one is a slightly different color. And we call these special name servers input delayed name servers. And as the name implies, they receive inputs with an artificially imposed delay. They also advertise their Anycast prefixes to the router with a slight, with a lower preference. So typically they don't receive any traffic. All the traffic is going to the top machine. However, when that top name server crashes, the monitoring agent will instruct it to withdraw its BGP advertisement, right? And now all traffic will start flowing to the input delayed name servers. At this point, DNS operations folks and engineers are on bridges identifying the issue, and the input delayed name servers are not consuming the new inputs until we've found out what the issue is, rolled back the inputs potentially, and fixed the issue in a widespread manner. And we've restored full availability of the system. This is an explicit design choice, I note, that we choose to answer DNS queries with stale inputs as opposed to not answer at all. So that's really a brief overview of Akamai DNS with a
Yeah, so we'll get started with the Q&A. That was great. Can you hear me?
Yeah.
Yes.
Okay. So, okay, so we have a couple of questions on Slack. So Dave Oran asks, is the load to the NS balanced with ECMP or something else?
ECMP, equal cross multipath. Yeah, that's what we use to balance, roughly spread the load uniformly between the name servers within a POP.
Okay. So Oliver Gasser asks, does Akamai DNS ensure that each domain has delegations to at least one POP on each continent or region? Or how does Akamai DNS ensure low latency to recursive resolvers?
So we advertise, or we try to optimize our Anycast advertisements of all of the Anycast prefixes across the world. So we do attempt to have good performance for every single Anycast prefix that each one of our customers' domains are operated on, yes.
Okay. So Lars Sprun, he starts with a compliment. He says it's a really interesting talk. And then he says, do you actively try to equally distribute load across POPs? If so, how do you optimize the prefix to POP mapping? Does the mapping change upon POP failure?
So on the first part, do we attempt to balance the load evenly across POPs? We don't, and one of the reasons for that is that the sources of load are not uniform to begin with, right? Some recursive resolvers actually, you'll note in the first section of our paper that we show that some recursive resolvers send far more DNS traffic than others, which is to be expected, I suspect. But as a result, if we were to try to make the distribution uniform across POPs, we would be providing potentially worse performance to some recursive resolvers because they would have to go to a distant POP, if that makes sense.
So rather than balance the load, I think the goal is really to have sufficient capacity to be able to serve. Balancing the load is not necessarily a good metric. You need to have sufficient capacity in all the POPs to serve everything well with low latency.
Right, and to that point, we do try to scale up the capacity in each POP for the traffic volume that it needs to serve.
Got it. So I had a question myself. Have you considered any proactive measures to reduce errors? So for example, we had a talk earlier on configuration errors with DNS, which won the best paper this time. So could you see a system like that being useful, or what kinds of issues might still need to be solved?
So, first, 2 points on that, I guess. Yeah, there is a lot of proactive testing that we do to avoid errors. That includes both configuration and in software, and yeah, in both of those things. And second, I think the paper you're referring to is Groot, and yeah, that's a very interesting idea and a great way to validate that even a correct DNS configuration doesn't lead to errors because of, say, some dropped or missing link in a DNS CNAME or DNAME chain. We don't use that today, but it's certainly something that we would pursue.
So let me then conclude with a more open-ended question on, we're all looking for research problems to work on. So what do you see as some open challenges that you'd like to see the community address based on your experience?
So one challenge is, of course, we have this big flowchart on how you debug problems, and it's almost entirely manual. We have this decision graph on how we debug problems to figure out what the right action would be, whether it's withdrawing routes or making other changes. Automating that, I think, is a huge, interesting open problem. And we do mention in the paper that that decision is really made manually, involving NOC personnel. And always the thing is to, can you do that automatically using, tools, telemetry tools, AI maybe.
I would add to that I totally agree with Ramesh first, but I would add to that two like subtopics that I think are particularly interesting in there. And one is that in the decision tree that we're mentioning, a lot of the information that goes into it to making those decisions comes from discussions with other peer networks on the internet, what they're seeing during an attack. And automating that process, I think, is an interesting challenge, some way to share that kind of information. And the other part would be that because Akamai DNS and many other large authoritative DNS like it use Anycast, really understanding how traffic will be rerouted to other places when we do take an active stance to make a change to, say, Anycast advertisements from one POP is also an interesting and active area for research to me as well.
Yeah. Hi, everyone. Please post your questions either on Zoom or in the Slack channel. Now, while people are getting ready with their questions, like in your longer talk, you talk about filters that are used for attack detection. Can you tell us more about that?
Sure. We've found that for certain types of attacks, it's possible to identify or detect the difference between legitimate traffic that the name servers are receiving, legitimate DNS queries that they're receiving, and the malicious queries that they're also receiving at the same time. So the name servers themselves have a front-end component to them which attempts to identify, really categorize the incoming queries as either legitimate or suspicious, and then prioritize the legitimate queries over the suspicious ones. And it does this based on a few features of the DNS queries that come in. So for example, we have sort of standard techniques like rate limits. We also have an allow list. So we keep track of what are the major sources of DNS traffic that we see over time historically, and we prioritize them in the future. Of course, those sources by IP address can be spoofed as well. So we have some more advanced features as well. For example, we've implemented hop count filtering. So we look at the IPTTL and we track that over time. And if it varies from what we expect from a major recursive resolver, say for example, something like Google Public DNS or Open DNS or something like that, then we deprioritize those queries as well. So each one of the filters is really designed to mitigate a specific type of attack. And we, in the paper, go into each one describing how it works and what it can mitigate.
Okay, thank you. And now we have a question on Slack. What are the occasions that the monitoring agent decides the name server on the machine isn't working properly?
So there's a couple of things the monitoring agent does to track and make sure the name server is what we call healthy. First and most simply is it makes sure that the name server is up, that the process is running. So if it's not running, obviously something's wrong and it withdraws routes. But it also does active probing of the name server by sending DNS queries for each one of the domains that Akamai DNS hosts, and then observing the response that we get back from the name server. There are also some more advanced features, including tracking the traffic that's coming out of the machine to make sure that the responses that we're handing out to legitimate queries that we're receiving on the platform are correct. And also we monitor the inputs that the name server is receiving. So we have inputs that we expect to receive at a fairly rapid frequency. And if any of those are stale, we detect that and we withdraw routes, assuming that the name server is unhealthy at that point as well.